So it can perform several arithmetic operations like addition, subtraction, increment, decrement, and comparison operation, right? And what are the logical operation of Pentium processor? There are four types of logical operations performed by Pentium processor, and these are logical AND, logical OR, logical XOR, and the last operation was logical NOT. Okay, so this processor support these two instruction also. One is called shift operation and another is rotation operation. Okay, so these are two additional operations supported by Pentium processor. One is called shift operation and another is rotate operation. And there are two types of shift operation. One is called left shift operation and its opcode is SHL. And another shifting operation is right shift operation and its opcode is SHR. And there are two types of rotate operation. One is called right rotation and another is left rotation. So ROL, it denotes to the left rotation operation. Okay, and another one is right rotation, ROR. So what is shift operation? In this operation, each of the bit is going to be shifted to the left side or to the right side. Suppose the syntax of this left shift operation is the opcode SHL and then the destination operand and the number of time you want to perform this left shift operation. This is the syntax of left shift operation. SHL, this is the opcode and the destination operand, and this is the number of time this operation will be performed. So suppose you have taken 8-bit register, that is SHL, that is opcode, and now the register is AL, and you want to perform this operation one time. Okay, so AL is 8-bit register. That means we can store 8-bit data. So there will be total 8 bits. And the bit position is from 0 to 7. These are the position of these 8 bits: 0, 1, 2, 3, 4, 5, 6, and 7. Okay. Now suppose the data is 1, 0, 1, 1, 0, 1, 0, 0. Okay. In this 8-bit register, this data 10110100 is stored. Now, this instruction is given to the processor SHL, AL, this is the AL register, and execute this shift instruction how many times? Only one time. So what is left shift operation? In this operation now, each of these bit is going to be shifted to the left side. Initially, the position of this 0 bit is 0, but after a left shift operation now, its new position will be 1. Then this bit will be shifted to the left side. That means in left shift operation, each of this bit will be shifted to the left side. Is that clear? What is left shift operation? Is it clear?
Yes, ma'am.
Yes, ma'am. Clear.
So now after this left shift operation, what will be the new content of AL register? This is AL register. That means it can hold how many bits? Maximum 8 bits. And these are the bit positions: 0, 1, 2, 3, 4, 5, 6, 7. Okay, so when the leftmost bit, this is the right, this is the least significant bit, right? And its position is 0. When this bit will be shifted to the left side, now an empty space will be created here. Now the new position of this 0 bit is 1, and then 0. For this 0 bit, the position is 2 now. Then 1, 0, 1, 1, 0. But now we don't have any space for storing this most significant bit. So where we can store this bit? After shifting all the bits from the right side, now we can see that we don't have any available space for storing the most significant bit 1. So at that time, this bit will be shifted to this carry flag. This is the carry flag, and this flag will hold the value 1. And after this left shift operation, this most significant bit will be discarded. That means the result or the data of AL register will be 0110100. But here in this position, there is an empty space. So this space can be filled up by adding a 0 bit. So this is left shift operation where all the bits will be shifted to the left side and the most significant bit will be discarded. Okay, and in this empty space you'll add a 0 bit. Is that clear what is left shift operation? So now if you want, you can change the number of times of this left shift operation. If we add 2 here, that means 2 times we need to perform left shift operation. So this is the result of first left shift operation. Then again, we need to execute the instruction. So at that time, after 2 left shift operation, 2 bit will be discarded. Okay, if the number of operation is 3, at that time 3 bit will be discarded from the left side. Is it clear?
Yes, ma'am.
Yes,
Yes.
ma'am.
Okay, then the next one is a right shift operation and its syntax is SHR, that is the opcode, and the destination address. After that, the number of operation done. Okay, so suppose this instruction will be executed 1 time. And so we can take any 8-bit register or 16-bit register. So suppose this in this register is stored the data AL. So now this is the register AL which can hold 8-bit data and the positions are 0, 1, 2, 3, 4, 5, 6, 7. So 0, 1, 2, 3, 4, 5, 6, 7. So this is right shift operation. That means now each of this bit will be shifted to the right side. In left shift operation, we started the operation from the right side, from the left, I mean the least significant bit. But in right shift operation, since you're going to move the data to the right side, we'll start from which bit? From the most significant bit. So this bit will shift it to the right side. And this is right shift operation. So in this right shift operation now, we don't have any available space for storing this bit. So that bit will be added in a carry flag register. This is the carry flag register. So now suppose the data is 0, 1, 1, 1, 0, 0, 1, 0. Okay, so what will be the result or what will be the content of AL register after a right shift operation? What will be the new content of AL register? There are total 8 bits and their positions are 0, 1, 2, 3, 4, 5, 6, and 7. So now this bit, its position is 7, right? It's going to be shifted where? In the right side. That means its new position is 6. Then 1, 1, 1, 0, 0, 1. So now the empty space is created where in the left side here you will add a 0 bit and this 0 bit is going to be stored here in this carry flag register. And now the least significant bit will be discarded. Clear?
Yes, ma'am.
Yes, ma'am.
So this is left shift operation and right shift operation of Pentium processor. The next operation is rotation. There are 2 types of rotate operation. One is left rotation, that is ROL, and its syntax is ROL destination operand and the number of time these operations will be executed. So ROL destination 1. So this destination operand can be 8-bit registered. So this is 8-bit register AL with 8-bit. So the bit positions are 0, 1, 2, 3, 4, 5, 6, 7. And the data is 1, 1, 0, 0, 1, 0, 0, 1. Okay. So now how this operation will be performed? This is a rotate operation, left rotation. So in these, this is just like the left shift operation. Okay, so all the bits will be shifted to the left side. So we can move all the bits to its, left side. So what will happen to this most significant bit? This is a rotation operation and it acts like a left shift operation. That means all the bits can be shifted to the left side. So these are the positions 0, 1, 2, 3, 4, 5, 6, 7. Okay, so the new position of this bit 1 is 1, then 0, 0, 1, 0, 0, 1. So in the right side now there is an empty space and we don't have any available space for 1. In left shift operation, we store that data in a carry flag register. In this left rotation also, the data will be stored by this carry flag register, as well as now this bit is going to be stored where in the right, where you can store it in this bit position 0. This is the difference between a left shift operation and a left rotation operation. In the left shift operation, when the empty space was created, we just fill that space by adding an extra 0. But in left rotation operation, that empty space will be filled up by that bit from this position 7. So we can add 1 in this position 0. Is it clear?
Yes, ma'am.
Yes, ma'am.
So what about right rotation operation? In right rotation operation, all the bits will be shifted to the right side. Okay, and in that operation now the empty space will be created in this position, isn't it? So that empty space will be filled up by the right, the least significant bit. So this is for a right shift operation. Now all the bits will be shifted to the right side. So what will be the new content of AL register after right rotation operation? Hello.
Yes, ma'am.
Yeah, what is the new content of AL register? Now shift all the bits to the right side. So the new content will be 1, 1, 0, 0, 1, 0, 0. And now this bit will be discarded in right shift operation, but in right rotation operation, we are going to take that bit from this position 0 and we can store it in the position 7. This is right rotation operation. Clear?
Yes, ma'am. Clear.
So this is all
Yes, sir.
chapter, sorry. Hello.
Clear, ma'am.
Okay, so this is all about chapter 4. Okay, now we can start the next chapter, that is chapter 5. I think you all are familiar with this data structure stack, and chapter 5 is all about the stack implementation. At first, we'll discuss about this data structure stack, that what is stack, how the data can be stored here, how many types of operation can be performed in this data structure stack, what is the difference between stack and queue, and the last topic will be how the Pentium processor implement the stack data structure. Okay, so what is stack? This is just a data container, right? This is a temporary storage of data, isn't it? This stack is a data structure which is used to temporarily store the data. What kind of data structure it is? We know that the data structure is of two types. One is linear data structure and another is non-linear data structure. So what kind of data structure it is? Is it linear or non-linear?
Ma'am, linear.
Linear. So why it is linear data structure? Because why it is called linear data structure? Because the data will be stored or removed in orderly manner. We can, all the insertion and deletions will be done by following some rules. That's why it's called linear data structure. And this data structure is called last in, first out data structure. That means that if you store a data, this is your data structure stack, okay? This is one end of this data structure, this is the other end. In stack data structure, one end will be open, another end is closed, right? And this open end is called the top of the stack. In stack, only one end will be used for insertion and for deletion, isn't it? Stack is a data structure where insertion and deletion will be done in only one end, and that end is called the top of the stack. And why it is called last in first out data structure? Because the data item which is inserted first will be deleted last. Suppose this is the top of the stack, so at first you inserted the data 1. So where will start it? Think about a linear array. Suppose this is the linear array data structure. Initially, the data structure is empty. Okay, but in array, we need to know what is the size of that array. Suppose the size of array is 5. That means it can hold how many data elements total? 5 data elements, right? If the size is 5, it will store 5 data elements, but the indices will be from 0 to 4, right? So how we usually store the data in array?
Basically,
this is the index 1, 0, 1, 2, 3, 4. Right, so if the first element is suppose 7, 7 will be stored where? In this position, isn't it?
Yes, ma'am. 0.
So 7, and then suppose 12, 15, then 10, 19. Okay, so this is a linear data structure. If whenever we want to store a new data element, at that time the pointer value will be incremented by 1. Okay, so what about this stack data structure? This data structure is called last in first out data structure. That means the item that will be inserted first will be deleted last. Okay, so suppose initially the stack is initially empty. So what will be the value of top? Top equals to 0, right? Suppose the address of this location is 0. And now, when we have a data element to store, at the time, the value of top will be incremented by 1, isn't it?
Yes, ma'am.
What? Yes. No. If we want to use zero-based indexing, at that time, when the stack is empty, the value of top will be -1. If we want to use zero-based indexing, if we want to use one-based indexing, at that time, the value of top will be 0, right? So we will use zero-based indexing. So when the stack is empty, at that time, the value of top is -1. Now, this is the first memory location with address 0. When we have a data to store, that is 7, at that time, this is our top, and the value of top is 0, okay? Now you want to store another data element, that is 12. At that time, and the value of top will be incremented by 1. So 0 plus 1, that is 1. Now this memory location here, this top will point to this memory location 1. Now top equals to 1. So look, we are using only one end for storing the data. Okay, now this is the top of the stack. 12 is the topmost element. At first, we inserted the data 7 and then 12. But now, when you want to remove a data from the stack, at that time, the last element should be removed first. We can only remove the data. Which one? We can only remove the topmost data element. And when top equals to 1, the data is 12. So at first, 12 will be removed from the stack. And then after a deletion operation, the value of top will be decremented by 1. Now the value of top is 0. So this is, and then we can delete it. So is it clear what is stack? It has two types of operation. One is insertion and deletion. And in this data structure stack, we can refer to this operation insert as push operation, and the delete operation is called pop operation. Okay. And when the numbers are deleted from the stack, the numbers will come out in the reverse order of insertion. So look at this figure. Initially, the stack is empty. Okay, so now after the insertion of 1000, this is the first element, and after inserting the element, this is your topmost element. This is the topmost element. Now, when you have another data to insert, that is 1001, at that time, you have to store the data item where? At first, the value of top will be incremented by 1, and then you can insert the data. So now this is the top of the stack. After that, suppose you have another data, 1002 to insert, then again, the value of top will be incremented by 1, and in that new position, you can insert the new data. Now, this is your topmost element. And the last data is 1003. Again, the value of top will be incremented, and this is now the topmost element. So this is how we can insert the data in a stack. What about the deletion operation? Look, at first you inserted this data element 1000, but now it's not the topmost element. So if you want to remove this element 1000, at that time, all the topmost element should be removed first. So the topmost element is 1003. After deleting it, this one will be the topmost element. Then again, delete 1002. Then it will become the topmost element. After removing it now, the stack has only one element, 1000, and this is your topmost element. Then you can remove it. Look at this deletion operation. This is a stack with 4 elements, right? And the removal should be done where you can remove the element from the top. So this is your topmost element. So after removing all the item now, the stack is empty. So what is the difference between this stack data structure and queue data structure? Stack is called last in, first out data structure, but queue is called first in, first out data structure, isn't it? And in stack data structure, we can use only one end, but in queue data structure, both the front end and rear end can be used. So in stack data structure, since the operation will be done in one end, that's why we need only one pointer, and that pointer is top. But in queue data structure, suppose this is a queue, and here we can store 4 to 5 elements, right? So in this queue data structure, one end will be used for insertion, and another will be deletion. Suppose this is our front end and this is the rear end. So in which end we can insert the new data, and from which end we can remove the data. Queue is called first in, first data structure. That is the data item that was inserted first now will be deleted first. Okay, this is the front end of the queue, and this is the rear end. So now which end will be used for insertion operation and which one will be used for deletion operation?
Front.
Sorry?
Front part.
Front.
Yes, ma'am.
Front for which operation?
Is it saying the first in, first out? So, ma'am, it will happen from the first.
Insertion on front side.
Insertion in the front side.
Yes,
Insertion
ma'am.
in the front side. Look at this. Suppose initially the stack is empty. There is nothing in this stack. Now, when you have a data to insert, at that time, after inserting a data element, suppose the address of the this data element is 0, right? Now you want to store another data element. Where do you insert it?
At the top of it.
There are total 2 pointers. One is the front pointer, another is rear pointer. Unlike stack data structure now, both of these end will be used for insertion operation and for deletion operation. Obviously, whenever you have a new data item to insert, the value of this pointer will be incremented, right? So now you have to expand your queue data structure, then you can insert the new data element 7. After that, suppose you have another data element to store, that is 10, and the value of this pointer will be 2. Still, we don't know which pointer it is. It can be front pointer, rear pointer. You have to decide it. And then the next data element is 15 and the pointer value is 3. That means every time when we are inserting new data elements, we are just incrementing this pointer value by 1. Okay. Now what about deletion operation? This is the first data element. That's why it should be removed first. Isn't it? After inserting 4 elements now, the value of this pointer is 3. Now you have to use another pointer for the remove operation. This is Q data structure. That's why the first element should be removed first. So at first 5 will be removed and then 7, then 10, then 15. Now tell me which one will be used for insertion operation and which one will be used for remove operation. Suppose this is your first data element, okay, and the index is 0, so 5 is stored here. Whenever you have a new data element, at that time the value of this pointer will be incremented, right? So this is your data structure Q with how many elements? Okay, suppose with 5 elements. So in which side we inserted the data? In the front side or in the rear side?
Rear side.
In the
rear side.
Very good. The insertion will be done in the rear side. Look, if you want, you can expand this data structure in this way. This is your first index 0, then 1, then 2, then 3, and then 4. Okay, so the first data element is 5, and then 7, then 10, 15, 20. So in this structure, you can say that we are inserting the data in the rear end. Initially, this was the first, this is the space of the first element, and now we are expanding this data structure. So we are inserting the data in the rear side. Suppose this is our rear side, and this is the front side. So for the new data element, the value of rear will be incremented by 1. When the Q has only one data element, at that time, the front pointer value and the rear pointer value is same. But at the time of insertion, the rear pointer value will be incremented by 1. That is now rear equals to 0 plus 1 equals to 1. But the front pointer value will be same, isn't it? After that, whenever you insert another item, at that time, the rear pointer value will be incremented by 1. Is that clear?
Yes, ma'am.
Yes, ma'am.
Is that clear? And now what about deletion operation? The deletion operation should be done from the front side. So at first 5 will be removed, and after the deletion operation, the value of front element will be incremented by 1. After removing 5, now 7 is the first data element and its position is 1. After the remove operation, the value of front pointer will be incremented by 1. Now 7 is the first element, so now we can delete it. This is our front element. After removing 7, now again the value of front pointer will be incremented by 1. So Q is a data structure where insertion is done in the rear end and the deletion will be done in the front end. Is that clear?
Yes, ma'am.
Okay, so now how we can implement this stack data structure in Pentium processor? What is the architecture of Pentium processor? It has 16 registers. 10 registers are 32-bit registers, and these are general purpose register, control register, right? And there are 6 16-bit registers, and these are called segment register. And the segment registers, their names are stack segment, data segment, code segment, and 3 extra segment, right?
Yes, ma'am.
Okay, so look at this here. We have to follow some rule for implementing stack in Pentium processor. The memory space reserved in the stack segment is used to implement the stack. The register, stack segment, and extended stack pointer are used to implement the Pentium stack. So we know that in assembly language program, there are 3 segments. One is stack segment, then the data segment, and another is code segment, right? So for each of these segments, some memory spaces are, allocated, isn't it? This Pentium processor has 3 segments. This is the stack segment, the data segment, code segment, and there are 3 extra segments: ES, FS, GS, right? And this is your assembly language program. It has 3 segments, that dot stack segment, dot data segment, and dot code. These are the directives, right? So when the processor will operate on the instruction and the data, at that time, at first we know that there are some internal registers. So the address of this segment will be stored in stack segment register, isn't it? The address of data segment will be stored here in the data segment register. But if we want, we can store the address of stack and data wire in the memory location. But at that time, the memory location, for each of the location, we need 20-bit address or 32-bit address. That's why we use logical form. So when we'll use logical address, at that time, the address of segment, stack segment, data segment, or code segment will be stored in the register. Is that clear? If we are using physical address, at that time, the address of stack segment, data segment, or code segment can be stored in the memory location. And for each memory location, there is a 20-bit address, physical address for 8086 processor, or 32-bit address for Pentium processor. But here we will store the addresses in segment registers, and the segment are 16-bit register. That's why we'll not use physical address, we'll use logical address, okay? And the next point is the stack segment register pointing to the beginning of the stack segment, and the extra segment pointer register giving the offset value of the last item inserted. So this is just a logical form of this stack data structure. So how we will represent a stack data structure? By using 2 values. One is the value of the stack segment register, and another is extended stack pointer register. Look at this figure. This is a stack which can hold maximum 256 byte data. Okay, so this is the capacity of this data structure stack. But initially the stack is empty. And how we can represent the data structure? By using 2 values. One will be the value, value of stack segment register, another is extended stack pointer register, right? So this stack segment register always points to the beginning of the data structure. So this is the first byte of this data structure stack. So this stack pointer will point to this, the first byte of the data structure stack. What about extended stack pointer? The extended stack pointer register giving the offset value of the last item inserted. Let me draw the figure. Okay, so initially the stack is empty. This is your stack, and how many bytes the stack can take? Total 256 bytes, right? So how we can assign the addresses here? Think about memory organization. How we graphically represent the memory address? Hello?
Yes, ma'am.
Suppose this is your computer memory. Okay, so now how we're going to assign the addresses to each of these bytes? There are supposed 256 bytes. So how we're going to represent this computer memory?
We'll start from 0.
Start from 0, right? That means here we are assigning some address from, in increasing order from the bottom to the top side, isn't it?
Yes, ma'am.
How we are assigning the address? The addresses are assigned in increasing order from bottom to the top side. So there will be total 256 bytes and the addresses are from 0 to 255. Okay, but when you will implement this data structure in Pentium processor, at that time, we cannot start from the logic, memory address 0. Read this point, the stack grows toward lower memory addresses. These are some rules for the implementation of stack data structure in Pentium processor. The first rule is the stack data structure will be represented by two values. One is the value of stack segment register, another is the value of extended stack pointer register. Okay, so this stack segment register will point to the beginning of the stack segment, that is from where the stack data structure has started. And what about the extended stack pointer? It will point to the item which was inserted last. Okay, from this extended stack pointer, we will get to know about the offset address of the last data element. Another rule is only word, that is 16-bit data, or double word 32-bit data will be saved in the stack. We cannot store a single byte, that is 8-bit data in stack. And the next rule is the stack grows toward lower memory addresses. This is the main point of stack implementation in Pentium processor. What is the point? The stack will grow towards lower memory addresses. What does that mean? That means we are going from the highest memory address to the lowest memory address, which means that the initial value of this topmost data element will be the highest memory address. Is that clear? This is the opposite of memory address assignment. Look, we are assigning the memory address in increasing order from bottom to top, but this stack grows towards lower memory addresses. That means we will store the first data element where?
At the top.
Hello. In the top of the stack, right? That means the first data element will be stored as a 256 byte of the data structure. Okay, and then after storing one data, now whenever you have another data item to store at that time, the value of this address will be decreased. Is that clear?
Yes,
Yes,
ma'am.
ma'am.
And another point is top of stack that always points to the last data item placed on the stack. And this topmost stack always points to the lower byte of the last word inserted into the stack. Now look at this figure. This is the stack and initially it's empty, but its capacity is it can hold 256 bytes. And the memory addresses are 0, 1, 2, 3, 4, 5, 6. And this is the highest memory. This is a byte with highest memory address, that is 255. So this is the beginning of the stack. So stack pointer will point to this memory byte, but the extended stack pointer will point to the offset address of the last data element. So this is initially empty. So actually the value of extended stack pointer will be 256. This is the topmost stack, which is a byte out of this reserved area. Total 256 bytes are reserved. It can be the byte 257, where you can add this topmost stack. I mean, this pointer is now point to the byte which is out of this reserved stack area. Okay, now suppose you want to insert a data element 21AB. This is hexadecimal number, and is it 8-bit number, 16-bit number, or 32-bit number? Look at this number 21AB. One rule is each of these byte, it's 32-bit data.
Yes.
Yes.
Why it is 32-bit data?
Ma'am, 16-bit.
Very good, 16-bit data. There are 4 hexadecimal digits and each hexadecimal digit equals to 4 binary bits. So there are total 16 digits, 16 binary bits. Okay, so this is a 16-bit data, or it's a word. So we need 2 consecutive bytes for storing the data. Look, when the stack was empty, at that time, the value of extended stack pointer was 256. This is a 255th byte. The address is 255. And this topmost stack now is denoted to a memory byte, which is 256. So whenever you want to insert a new data element, at that time, the value of extended stack pointer will be decremented by 2. Why it will be decremented by 2? Because for storing this data, we need 2 memory bytes. Is that clear?
Yes, ma'am.
Yes,
So
ma'am.
this 21 AB is your lower byte and 21 is the higher byte,
Higher
isn't
byte.
it? So now at first the content of higher byte will be stored. So 21 will be stored and then the content of the lower byte will be stored AB, and this topmost stack will always point to the lower byte of the word. That's why now after inserting a word that is 21 AB, the new value of TOS is, what is the new value? 254. The address of this byte is 255 and it's 254. Is that clear? So look, now
Yes, ma'am.
whenever we're inserting new data element in the stack, that means the stack is expanding but towards the lower memory address. Initially, when the stack was empty, at that time, the value of topmost stack or extended stack pointer was 256. But after inserting a data item, although the stack is expanding, but it's expanding towards the lower memory address. The new value of extended stack pointer is 254, which is the value of topmost stack, and the address is 254, which is less than 256. Okay. Now you want to insert another data element, that is 7FBD329A. Now, is it a word or a double word? It's a double word. There are total
Double word.
8 digits and each digit equivalent to 4 binary bits. So there will be total 32 bits. That means it's a double word. So we need how many consecutive memory bytes? 4 memory bytes, isn't it? That's why the value of extended pointer will be decremented by 4. The new value of extended stack pointer is now 250. Okay, look. That was the last addition. I mean, we inserted 21 AB in this data structure. Now we are going to insert all these 8 digits, right? At first 7F will be inserted and then BD 329A. And we know that the value of this topmost element will always denote to the lower byte of the inserted element. This is the lower byte. Is it clear how we can implement the stack data structure in Pentium processor?
Yes, ma'am.
Is it clear? I'm giving you another example, okay? So this is a stack which is initially empty and it can hold total 10 bytes. So we can represent this data structure by using 2 values, that is stack segment number as well as extended stack pointer value. Okay, so this is the first byte and its address is 0, 1. We are assigning the address in increasing order from bottom to top. 4, 5, 6, 7, then 8, 9, and this is 10. Okay, so initially when the stack is empty, at that time the value of top of the stack will be assigned to a memory byte which is out of the reserved stack area. This is the reserved, sorry, no. This is the reserved stack area from 0 to 9. Okay, now this topmost element is pointing to this memory byte which is out of the stack. Is that clear?
Yes,
Yes,
ma'am.
ma'am.
And the value of extended stack pointer will be equals to the value of this topmost stack. So initially the value of ESP is 10. Okay, what about stack pointer? This stack pointer always denotes to the beginning of this stack data structure. Now you want to insert a data element 7. Is it possible? Is it possible? Suppose this is a hexadecimal number 7H. Can we insert 7H in this data structure? structure. Is it possible or not? Or okay, the value is 07H. Hello?
Yes,
Can
ma'am.
we
Possible.
store 07H?
Yes, ma'am.
Yes, sure. One rule is each of these, I mean, in this stack, we can store a 16-bit data, that is a word, or 32-bit data. So this 07 is not a word or it's not a double word. So we can store it, okay? So now we want to store 3AB7. So is it a word? Yes. This 3AB7 is a word. And this 3AB7 can be stored as 16-bit number, and this 8 bits from 0 to 7, this is the lower byte, and this is the higher byte. So if the newest element, if we want to insert a 16-bit data, or for storing the 16-bit data, we need total 2 bytes, isn't it? What is the value of stack pointer now? 10. So this stack pointer value will be decremented by 1 now. The new value of extended stack pointer will be 8. Okay, as well as the value of topmost stack will be 8. That means at first we will insert 3A and then B7, and always the topmost element will point to the lower byte of the inserted element. This is the lower byte. So now the new value of extended stack pointer is 8. And this is our stack segment register. Is that clear? So when we are
Yes, ma'am.
inserting a new element, at that time, the value of extended stack pointer will be decremented. Okay, it will be decremented by 2. If you want to insert a 16-bit data, it will be decremented by 4 if you need 4 bytes for storing a double word. Okay. And look, we know that in Pentium processor, how we can implement the stack data structure. If we want to expand it, if we want to add new data element, at that time, it will expand towards lower memory address. So when the stack was empty, at that time, the value of extended stack pointer was 10, but now the value of extended stack pointer is 8, which means that this is the top of the stack. Okay, now after that you want to add another element, which is a double word. So there will be total how many elements? 4 hexadecimal, sorry, there will be total 8 hexadecimal digits. Suppose 17B48097. So this is 8-digit hexadecimal number. That means we need total 32 bits or 4 bytes. So we need 4 consecutive bytes for storing this hexadecimal number. At that time, the value of extended stack pointer will be decremented by 4. That means after inserting this new element, the topmost data element will be this one. So the addresses are 0, 1, 2, 3, 4, 5, 6, 7, then 8, 9. So 3A, B7. After this insertion, this content, this was our topmost element. B7 was the topmost element with memory address 7. But now, when we want to insert a new element, at that time, the value of extended stack pointer will be decremented. So it will be decremented by 4. So 8 minus 4 equals to 4. That means it will be the newest topmost element. Now, after this insertion, this is our topmost data element. Okay. So at first we'll insert 17 and then B4. After that 80 and 97. So this is our topmost data element, and it's the value of extended stack pointer. So extended stack pointer equals to 4. Is that clear?
Yes, ma'am.
So this is the insertion operation on in stack data structure. We call it push operation. So what is the syntax of push operation? The syntax is push and then the stack operand, sorry, the source operand. This is the syntax of push operation. So what is pop operation? Pop means deletion, right?
Yes, ma'am.
So how we can delete the data from stack data structure? Look here, we are not only discussing about the push and pop operation of stack data structure. This topic is the Pentium implementation of the stack, that how the Pentium processor deal with the data which is stored in that data structure stack. That's why we need to, we're concerned about the memory addresses also, because this is Pentium implementation of the stack. So this is the figure for push operation. For push operation, at first we need to create the space, right? We need to find out which one will be the newest topmost element after that insertion, right? And if we delete, if we remove, decrement the value of ESP, we'll get to know about the newest topmost element. But what about pop operation? Pop, that means you'll delete some elements from the stack. But stack is last in first out data structure, that means the topmost element should be removed first. So I think in the next class, we'll discuss about the pop operation. Clear?
Okay,
So
ma'am.
do you have any question in stack data structure? That is, what is stack, or how the data will be stored and removed, or how you can implement it in Pentium processor? Any question? No question. That's great. Okay, then thank you.
Ma'am, I
Thank you,
missed my,
ma'am.
Sorry?
ma'am, I missed my attendance.